Hi guys, Stupid Simple here, where I take topics that make me feel stupid and try and turn them simple. Today, I'll be talking about differentiation. The goal is this will be the first video in a series of videos covering differentiation for a high school level. We're going to start here with the proof and general definition of what we mean to differentiate, and we'll move forwards from there to go through the power rule, chain rule, product, quotient rules, give some specific examples, and go through some work along the way, building up to what the goal of doing just one long, big video, kind of blue pen, red pen style, a bunch of different questions, a bunch of different examples, so you can practice as much or as little, but preferably as much as you like, so that you feel confident with all the individual parts and putting them together. So, let's start. I think, personally, the best place to conceptualize what I mean with differentiation is to start from middle school to early school, finding the gradient of a slope, because that's really what we're doing. So when you're in early-ish schooling days, what you do to learn to find the gradient of a slope between 2 points is you take any point, say here and here. Let's give them arbitrary coordinates. Let's say 5, 3 for this one, and I don't know, 4, 2 for this one. It's arbitrary, they're pretty close, doesn't really matter, it's just the idea of the process that we want here. If we want to find the average slope, which is to say the gradient of this line, what we want to do is we want to take the difference between the two of them along their x coordinate and the difference between the two of them on their y-coordinate and divide one by the other. So this value here is just the x-coordinate of this point minus the x-coordinate of this point. So that will therefore be 5 minus 4, which equals 1. And the value of this point here will be the same idea, this coordinate minus this coordinate, which is 3 minus 2, which equals 1 as well. To then find the gradient, all we do is take the difference in coordinates of the y divided by the difference in coordinates of the x. So that is therefore d, or difference, in y divided by d, or difference, in x. Our dy is 1, and our dx is also 1. So we have a gradient of 1. It's not a very good diagram. I'm not exactly very good at drawing, but you get the idea. That's the process. That's what you used to do in middle school. That's fine. That works for this situation and for this kind of setup, which is great. This is all we need for now. So, why would we do anything else? But it doesn't really work long term. We quickly run into some issues for these kind of techniques. The first and arguably most major is that it relies on having 2 points. It's also not very good for answering questions you'll find in exams, and it's just generally a bit inaccurate, shall we say. The blue line was not the same as the red line, etc., etc. So, what do? How do we make things better? Well, what we're going to do is we're going to work towards finding the formal definition of the gradient of a line at a point. And to do that, we're going to have to be comfortable with just a little bit of terminology for now. All I'm really going to care about you knowing is that when I say d, I mean difference. And when I put a triangle, I mean d, which means, you'll see why in a second, but really all I really care about is that triangle is just change or slight difference or small perturbation, if you will. We'll get back to that in a second. But for now, what we're going to do is we're going to do the exact same process as before, but instead of having 2 points given to us, we're going to say at some given point here, I want to find the gradient of the line. And to do that, instead of finding a second point and comparing a line between them, I'm going to take exactly the same, another point between the 2 lines. Except instead of going all the way up here, I'm going to zoom in a bit. And a bit more, and a bit more. In fact, I'm going to zoom in as far as my computer will allow me. That's good for now. and I'm going to draw this point here. Can you see that? Yeah. The coordinates in these don't really matter. What matters is that I'm looking for basically the gradient of this line. Because when you zoom out back to the rest of the diagram, the curve, D and D, whatever else, there we go. It's the same point. It's basically the same point. And I know you may be wondering, basically the same point and actually the same point are not the same thing. No worries, we're going to get to that. So how do we find the difference between these? How do we find the gradient between these two lines? Well, let's take any point that we like, and let's just call it x. I've added a little bit to it, going up the line upwards. So let's just call that x plus some change in x, or plus some small difference. The distance between the 2 points is what my triangle is. That's just triangle, difference, change, perturbation, whatever. What do we do again? Well, then we minus the coordinates of the other part. We're going to take away x. And then we're going to rescale the whole thing by a change in x. Because, that accounts for the zooming effectively. So what we now have is a definition. We basically want, as this change in x gets smaller and smaller and smaller, that this holds. Because that's exactly the same process that we did before. So what we're looking for is the limit, or the lim, as change in x goes to 0. When this is 0, this is true at a single point instead of being relatively close. Just for sake of ease, I'm going to call change in x h, because writing one thing is easier than writing two, and it's generally accepted. You might see it come up in textbooks and such. So let's rewrite this. For whatever the function here, whatever the line is, whatever the equation is, the function f of x plus h, the difference in x, minus the function of x divided by h. If we take a limit as h approaches 0 of this term, we get the change in y dy by the change in x dx, which equals the gradient at whatever point x we chose here. I guess if you want to take a screenshot, I should just say that this red line is the line y equals f of x, some function x. This is the formal definition, this is what we're actually doing, and this is kind of useful, if just for the sake of knowing what you're doing and why you're doing it. But it's a little bit easier to see what we're doing if we give a few examples and go through ourselves. So let's do exactly that. Let us come here with a pretty crudely drawn but attempted y equals x squared. So now what we're going to do is we're going to try and differentiate this line y equals x squared using the formal definition. So first of all, let's write out the formal definition in its full, in terms of h at least, which is the limit as h goes to 0 of f of x plus h minus f of x all divided by h. we now substitute in the value of our line. So in this case, y equals x squared. So anything that happens to the x happens to an x plus h. So now we're taking the limit as h tends to 0 of x plus h squared minus x squared over h. We can do some algebra here for, it's probably quick if I just type lim, of h goes to 0. Let's do a bit of binomial expansion of x plus h squared. So that becomes x squared plus 2x h plus h squared minus x squared, all divided by h. The observant among you may notice we have an x squared and a minus x squared, so those two cancel. And doing a little bit more algebra, we can divide the bottom, we can take out the division of the h here by taking out this h and the squared. This leaves us with the limit as h tends to 0 of 2x plus h. And now, as we can see, as h goes to 0, this term h, well, it goes to 0. And therefore we're left with the gradient of this curve at any point, dy by dx equals 2x. For those of you who know how to differentiate ahead of time and are a little bit more comfortable with the power rule, you will have seen this instantly, but for a formal definition, this is correct. It's a bit slow, it's a bit painful, but it is correct. Let's do an example or two so you get a bit of a hold over it, and then hopefully this will make a little bit more sense. Go over here. You may be asked in a textbook to say, find the gradient of a curve y equals, let's say, 4x cubed at the point x equals 2. Point x equals 2. So we're going to do exactly the same logic as before, but this time we are not going to draw a graph because I can't draw that well. But the same logic will apply. Let's write out our formal definition first. So we have the limit, let's say, dy by dx equals the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. We'll substitute in our expression for x, in this case 4x cubed. So we'll find the limit as h goes to 0 of 4x plus h all cubed minus 4x cubed, all divided by h. We'll expand these out again, which gives me the limit as h goes to 0. x plus h cubed we'll do first, so we'll say 4, because it's the harder bit. X cubed, 3, plus 3x squared h plus 3x h squared plus h cubed minus 4x cubed, all divided by h. Working from the top up here now. We can simplify further. That gives us the limit as h goes to 0 of 4x cubed plus 12x squared h plus 12x h squared plus 4h cubed. Just move me over a little bit, so I'm not squeezing everything in too badly. Minus 4x cubed, all divided by h. We could simplify things a little bit here. 4x cubed minus 4x cubed. And we can take an h away from each of these individual bits. So that disappears, the 2 disappears, and the 3 here becomes a 2. So now we're left with the limit as h goes to 0 of 12x squared plus 12x h plus 4h squared. Now, since h is going to 0, all the things with h's in them say goodbye. And therefore we're left with the gradient dy by d, oh, that's a terrible d, by dx equals 12x squared. All right, we've differentiated. And all that's left now for the question purposes, arbitrarily chosen, is just to substitute x equals 2 into this bad boy here. And we'll do exactly that. 12 times by 2 squared equals 12 times 4, which equals 48. And that's all there is to it. It's a bit tricky, especially seeing all of these numbers and all of these symbols and all of these x's and h's and things that seemingly come out of nowhere. But if you just think we're just taking the difference between two very close points and trying to find the angle as you would, you can see that the real level of maths in this is not too high. But even so, if there are parts of this you found tricky, let me know. I'll be more than happy to go through it again. If some of the indices rules may have confused you, like the divisions by h, or if maybe there's a bit of binomial expansion, like when we went through 4x plus h cubed and got this big thing over here. If that was tricky, let me know. I'll gladly make a video on those. If you thought this was a bit simple, that's absolutely fine. It'll be great to move on to the next few videos after this. But in the meantime, I'm Stupid Simple. This was the proof and definition of differentiation. I hope you enjoyed and found that simple, right?